so that we have ample time for question and answers. Um, Yesterday, we started discussing non-locality and we gave two examples of non-locality. And I asked if anyone would like to do this as a homework problem. In fact, I did the homework myself. And I just wanted to start off by sharing a clearer picture of the probability boxes experiment that we discussed yesterday. So, in front of the screen, there is a description of the example of non-locality I gave yesterday. It's also been posted on the Google Classroom. So let's go through this step by step in a methodical fashion so that we can reiterate what we learned yesterday and look at some interesting aspects of the non-locality concept. So I hope you can all see the screen right now. Is the screen visible?
Yes, sir, it is.
Okay, okay. So we started off by looking at two boxes, Alice and Bob, and each one of them has an input X and Y and an output A and B, and each of X, Y, A, and B is a classical bit 0 or 1. And the promise is that Alice and Bob play the game in such a fashion that the product of X and Y equals the exclusive OR of A and B. So So Alice and Bob meet, they decide the protocol, they decide the rules of the game, and then they depart. They move apart and they perform the experiments. They look at the outcomes of the experiments and then they share the results with each other and see how many times they've won. So this is the overarching theme of the game and the rules that they would like to maximize their chance of winning. Okay. So the rules of the game is that Alice and Bob get together. uh, Alice proclaims, so if you look at the left box here, Alice proclaims that x equals 0 would, if she gets x equals 0 as the input, she will churn out a equals 0 as the output. Okay. Bob is just sitting next to her and he says, okay, if y is my input, then I will put b as equals 0 as my output because that would ensure that we win the game. Okay, then Bob takes a step forward and proclaims that, all right, if I get the other input, y equals 1, that I will still churn out b equals 0 because that will ensure that with x equals 0 and a equals 0, which Alice has already decided, we still win the game. But then Alice is left with no other choice. Alice is left, in fact, with two choices. For x equals 1, she can either put b equals 1, which is in the left box that you see, or she can put b equals 0, which is in the right box that you see. So these are the only two options that come out as candidates for increasing the likelihood of winning the game. But the left box ensures a probability of success of 75%, and the right box, the rules laid out in the right box promise a probability of success of 50%. So the maximum probability of success is 75%. And that's the best that you could do with local realism without communicating your results to between Alice and Bob. Alice and Bob are separated out. This is the best you could achieve classically. But then enters quantum mechanics. And quantum mechanics, as you know, gives you all kinds of strange results. So now Alice and Bob still they get together. An entangled pair of particles is produced. Alice gets one particle of the pair, Bob gets the other particle of the pair. And the particles are prepared, say, in the Bell state 0, 0 plus 1, 1. And Alice and Bob now design a different kind of game. They still would like to maximize the probability of winning. So now Alice says that if for my two possible inputs, which are totally random, I could either get x equals 0 or x equals 1 as my input. But then, depending upon the value of x, I will choose a different basis. If x equals 0, I will choose the rectilinear basis, the ket 0, ket 1 basis. And if I get x equals 1 as the input, I will choose the diagonal basis, the 45 135 basis. And Bob says, all right, I'll do a similar treatment. If my input y equals 0, I'll choose a basis that is slightly tilted at 22.5 degrees. And if I were to get y equals 1 as my input, I will choose another tilted frame basis in which my tilt is minus 22.5 and 67.5. So, so they decide on the basis, and then they make partition with one another. They move separately, they move far apart, and then their inputs start coming in. The inputs are just random streams of zeros and ones, and then they note down the results of their final answers, their A's and their B's, and then they get together and compare the results and find out that the probability of success has gone further beyond 75%, so that they have increased the likelihood of their success. And then I asked you to make a table which just brings home this idea quantitatively. So x and y could be 0 0, and a and b could take four different values for this particular combination of x y. And we know that some of these games, some of these trials will give you a success, some of these trials will give you a failure. And you calculate the probability of all the successes, and then you add up all of these probabilities and you get the final result. So I've repeated this calculation for all the successes. I don't need to repeat them for the failures because they don't contribute to the probability of success. And we looked at one example of this calculation yesterday. And So, do you understand? Does everyone understand how this table is constructed? Any one or two votes of confidence? Okay. Okay. Rand Alpha, Rand Jibreen, Madiha Khalid. Yes. Okay. Thank you. So, I've calculated these probabilities. So, just as an example, the probability on the screen, you will see that if the input is 0 on both x and y, I would like to find out the probability that a and b both are 0. So x equals 0 and y equals 0 ensures that Alice uses the 090 basis and Bob uses the 22.5 112.5 basis, and the output 0 on each of a and b implicate that the detector that is aligned with the cat 0 axis for Alice and the detector that is aligned with the 22.5 degrees axis with Bob fires. So I need to find out the overlap of the input state, the bell state 0 0 plus 1 1 with cat 0 crossed with the 22.5. And I do this calculation and my answer is half cosine squared pi by 8. Likewise, I've done all of these calculations and each one of them turns out to be half cosine squared pi by 8. And then I also find out all the probabilities. And it turns out that for some cases, even though I win the game, but there is zero probability of winning the game in that manner. So if you notice x equals 1, y equals 0 with inputs, and the outputs a equals 0 and b equals 0 is on the table is this particular row, the top row that you see on the screen at the moment. But so this ensures winning the game, but the probability of this outcome is 0. So overall, there are some successes, but those successes are improbable. You cannot win the game by that mechanism. So I do all of these probability calculations and then I add them up. So I have four probabilities. Each one of them is half cosine square pi by 8. But then the inputs, there are four different kinds of inputs. X, Y could be 0 0, 0 1, 1 0, and 1 1. So with each probability, I have to pre-multiply with a factor of 25% of 1 by 4 because the probability of each particular input x, y is a quarter. So when I do all of this calculation, my answer is 2 plus under root 2 over 4, which is greater than 3 over 4. So this shows that with the help of quantum mechanics, what we could do is that two parties use entangled particles, and then they separate out. They go far apart. One goes on to Jupiter, the other goes on to Mars or remains on Earth, and they perform, they run, they get different inputs and look at their outputs, and then when they reconvene and share the results over a classical channel, their outcomes defy the classical probability. They go beyond the classical probability, even though the systems are not communicating with one another after they have separated out. There is no possibility of superluminal communication, but this has this ghost like effect that these two entities are communicating with one another in a strange fashion. This baffled Einstein, Podolsky, and Rosen. This baffled Einstein. How is it possible that two entities that are separated far apart, the outcomes of one which are totally random based upon random inputs, and the outputs of another which are totally based on random inputs, they show such a strong correlation? So this is called non-locality. Even though the entities are not communicating with one another, still there is a stronger than classical correlation which comes out due to this resource that we call entanglement. All right, and the other example that I gave yesterday was about looking at the Hardy's theorem, and having a state called the Hardy's state and looking at the probabilities. Classically, the probability of a particular outcome, if we were to believe in local realism, if we were to believe in causality, were zero. But then we did a calculation and we found out that we still get a non-zero finite probability of of a particular event. So this is the idea of non-locality, and non-locality has an important role in different practical quantum cryptography and quantum communication strategies. So at this moment, I would like to pause and take some questions. So any questions? I'll just take a 30 seconds break to invite any questions about this.
Can you share these papers with us?
Uh, yes, it's already on the Google Classroom. It's already uploaded there. So any questions?
Assalamu alaikum. I have a question that
Yes.
is related to measurement. Now, if we know that due to superposition, when we measure a qubit, the two measurement devices can give different results. But if we're measuring absolute zero, for example, zero ket on Z basis, but the measuring machines are different, but they're both based on Z basis. So can we say that with 100% certainty that both will give zero, or if there'll be any noise or any error which can cause a problem in that? Two different measurement devices, both on Z basis, and both are measuring zero ket. Any practical limitations or not having zero as a result?
Uh, if I have understood your question properly, all of the discussion that we're having so far are ideal quantum measurements. It is possible that there are two devices. Even if you don't have two devices, you have a single device that is prone to all kinds of errors. It's prone to noise. For example, if I talk about a detector, so here's a detector, and a photon comes in, and this is a single photon detector. A single photon detector, which is required for most quantum computing experiments based on single photons. And this photon is in a particular polarization state. If this detector clicks, we would say that the polarization of the photon is ket zero. But it's well nigh possible that even in the absence of a photon, this detector clicks, because eventually this detector is a p-n junction, and the how a photodiode works is that a photon comes in, it lowers the barrier, the energy gap, and electrons start to flow. So a single photon detector is activated by just a single photon, but electrons are always there. and this detector is at some finite temperature. So electrons have some noise, which is called Johnson noise. So even in the absence of photons, there will be what are called dark counts. So there will be accidental positives, accidental registrations, and these accidental registrations contribute to noise. There could also be missed positives. That is, a photon comes in, but the photodetector does not trigger because it's within its refractory period, which means that it has earlier detected a photon and it's not yet ready to accept the second photon. So there is always noise, and there are accidental coincidences, false positives. So your experimental signal has to be above this noise limit. But all the results that we are discussing so far, they are for ideal measurements. But for real measurements, when you go into the lab, you have to take into account noise. So a signal to noise with single photons should be above a certain threshold. I hope I've answered your question, and I hope I've
Uh,
understood your question in the first
yes,
place.
yes, yes, perfectly. Thank you so much, Dr. Sabi.
All right, so let's move on. So today is our last lecture, and you're welcome, by the way, to give feedback to Mosina about this lecture series, and uh, we are also planning to do more lecture series in the past. So you're welcome to write to us about suggestions and about comments and feedback about this particular lecture series and any other future lecture series you would like to be beamed on the platform of the Khwarizmi Science Society. So lecture 8, in lecture 8, I will be dealing with a quantum cryptography mechanism, and the particular protocol that I will exemplify is called the BB84 protocol, because it was invented by two scientists, Brassard and Bennett, in the year 1984. Now, how does traditional cryptography work? So let me just give you an example of traditional cryptography that will help us understand better how quantum cryptography can help. So let me just lighten my pen a little bit. So traditional cryptography, most cryptography schemes such as RSA work on the idea of private key encryption. And let me give you a simple example of that. Excuse me. Suppose we have Alice and she would like to send some message to Bob. The message is a stream of zeros and ones. Say 1011010. She would like to send out this message to Bob and she would like to encrypt this message. So, what she would do, she would create a secret key or a private key. Okay. And she will tell that key to Bob. So, the key that she will create, let's label it by X, is also a string of random zeros and ones. Now, this originally, what I've written here at the top, this is a message that Alice would like to convey. This is the real message. And now she creates a key which is totally random. It has to be random. Okay, a random string of zeros and ones. Suppose it is one, sorry, excuse me, 111010001. So this is a random string of zeros and ones. So this has to be created by a universal random number generator, which creates truly random bits. Now what Alice does, let's say that her initial message is labeled A. What Alice does is that she does the exclusive OR of A and X bit by bit, right? And we already know how exclusive ORs work. So, can you just speak out or tell me what the result of this bitwise addition would be between A and X?
0 1 0 1 1 0 1 1 0
Zero. Is zero
1.
here? Okay, okay. All right, so this is the encrypted message. And of course, it's different from the original message that is was intended to be sent. Okay. And this encrypted message, by the way, is totally random because the key is random. Okay. Since the key is random, the encrypted message is random. Now, this message is sent to Bob. Okay. If this message is sent to Bob, what Bob does is he takes the encrypted message, the apparently random message, and the apparently random message and takes the exclusive OR of the message with the key. Now, the key has been shared between uh, Alice and Bob. It's a private key that Alice made, and it is shared on a private channel with Bob. And so first of all, let's see what is the result of the exclusive OR of the private key, which is shared with Bob. Remember that this private key is also shared with Bob. So Bob gets a copy of the key as well. So what is the result of the exclusive OR of the key with the message? It's 1 0 1 1 0 1 0 and 0. And is this the same as the original message? Yes,
No.
it is. Yes. So this is the original message here. And the retrieved message, Bob has retrieved a message which is identical to the message that Alice wanted to send. So, with the help of this private key, Alice and Bob can communicate messages which look totally random, but they carry some meaning. So, the original message Alice wants to send is not gibberish, it's not random, it is a sequence, well thought out sequence of bits of zeros and ones. And Bob recovers this on his hand, provided that Alice and Bob share a private key. And this key has to remain secret between Alice and Bob. So the problem with this scheme is that if there is an eavesdropper, so I'm using this word eavesdropper. You might not know this word, but it's used in literature. An eavesdropper is like a hijacker who would like to intercept these messages, who would like to change the messages, or who would like to withhold information between Alice and Bob, who would like to corrupt the messages or make them erroneous, change a bit flip. So left goes right, north goes south, and so on, change the 0 to 1. So he's an hijacker, an evil guy who is bent upon disrupting the communication between Alice and Bob. So if an eavesdropper who's normally goes by the name Eve would like to intercept this communication, Eve would be looking out for the private key. So if the secrecy of the key is compromised and Eve gets to know the key, he can look at the message, he can read the messages himself, right? And he can transmit a new key to Bob because he's already intercepted the key. So we would like quantum mechanics to help. We like quantum information to help. So this is what this is what the BB84 protocol does. So I think my video uh, is not working. So give me a second to correct the video. Just hold on, please. So in the meantime, you can ask any questions if you like.
I have a question.
Yes, please.
A plus X. This information with who?
Uh, just a minute. Just a minute. Let me just give me a second. Let me restart my
Yes,
camera. Just
please.
let me. So can you repeat your question, please?
Yes. The information of A plus B. Who have this?
A plus B or A plus X?
A plus X.
A plus X. So all right. Okay. So let me draw a diagram. This is Alice and Bob. So Alice wants to send out a message A, some string. Okay. She has a key. She makes a private key X. This is totally random. And she shares that key prior to communication with Bob. So Bob has a copy of the key. All right. So both of them have a copy of the private key. Now what Alice does is that she creates A plus X, which, let me do it again, 1 1 0 0 0 1 0, and this is the message that is transmitted to Bob. This is the scrambled message or the random message, apparently random message that goes to Bob. This is the desired message. Okay, so Bob gets this message A plus X, and then finally what Bob does, finally Bob does an exclusive OR between the message he receives and the key. Okay, when this exclusive OR is done, you get a 1 here, 0 1 1 0 0 1, and this is turns out to be the same as A. Okay, so I hope this explains your question and answers your question duly.
Yes, completely.
Okay, good. So any more questions? Okay, just give me a second. There's some problem with my phone. Just a minute. Like to talk about the BB84 protocol. Now, the BB84 protocol is quite interesting. I'm making one last attempt for the camera. Just a second, one last attempt.
What the benefits? And is there any experimental, lab experimental, we use this?
Yes, of course. first of all, if you directly send the message A, this is the message A. If you directly send this message A, which is your desired message, then it's being sent on some channel, and generally it's being sent on a classical channel. So there are always eavesdroppers, there are always hijackers, someone who would like to read your message. You want to keep your message secret. So how do you do that? You make a key, a private key, and you use that key to encode your message. So your actual message that you send becomes A plus X, and this looks totally random. Okay. Suppose
Okay.
your A was just a string of zeros, but your X is totally random, so your A plus X appears totally random. So from random information, it's very hard for an hijacker to extract useful information. You just get a sequence of random zeros and ones, and no, does not carry any information content. So that's why you would like to encrypt your message, your orderly message, into into an apparently random message, and that is done with a random key. Okay, and
Okay.
so this is done in the conventional setting, but in the quantum mechanical setting, you would, because if Eve can always hijack your key. The problem is that it's difficult to keep the key secret. So if Eve gets to know what the key is, he can decode the messages, because Bob can decode the messages, so can Eve. So you would like to keep the key secret. But quantum mechanics, and okay, and if Eve intercepts the message and reads the message, still the information, a copy of the information, is going to Bob, and Bob is deciphering and recovering the message. Bob cannot tell whether there was some Eve or hijacker in between, so he is unaware of the presence of Eve. Okay, so
Okay,
now
I see.
what quantum cryptography does, and the BB84 protocol ensures, is that at least Alice and Bob know that an Eve exists, and an Eve is trying to hijack the information, and the Eve is intercepting the information. Okay, and let me show you how this is achieved. This is slightly tricky, but not that tricky, and I hope you'll be able to understand. So what's happening is that there's an Alice and there's a Bob, as in the usual setting. Alice and Bob. Okay, so Alice would like to send some messages to Bob. Okay, so Alice comes up with her rules or scheme. So Alice has some input variable X, just like a key, and this X could be 0 or 1, totally random. Okay, and what 0 means is the following. Alice Alice is preparing photons. So now instead of sending classical bits, Alice wants to send qubits in a particular state to Bob. So there are photons traveling from Alice to Bob. Okay. Now Alice has a random number generator, or an input, a random input X, that can take two values, 0 and 1. If X is 0, then Alice prepares a photon either in the vertical polarization state or the horizontal polarization state, which means that if she would like to send a bit 0, she will prepare a photon in the state 0, and if she would like to send a bit 1 with an input X equals 0, she will prepare a photon in the state ket 1. Cat 0 is horizontally polarized, cat B is vertically polarized. However, if Alice Alice's input, which is a random number generator, comes up with the value 1, she chooses another basis, and that is the diagonal basis. And if she won't like to send a bit 0, she would prepare a photon in the state 45 degrees. And if the bit is 1, she would like to send a photon in the state 135 degrees. So, just for your reminder, cat 45 degrees is a shorthand for, okay? And some authors represent this as an arrow that is tilted at 45 degrees. And 135 degrees is 1 over under root 2, okay? So 45 degrees and 135 degrees are shorthand for these superposition states. So suppose Alice wants to okay, I'll give you more examples of this. So Alice prepares photons, and she wants to send a stream of zeros and ones. So she prepares photons according to this scheme, and photons are prepared at regular intervals and they are sent to Bob. So these photons go to Bob. Photons which could be in the state 0, 1, 45 degrees, 135 degrees. These photons are going to Bob. Now, Bob also has a scheme. Bob also uses a random number generator that can take up two values 0 and 1. So Bob does a measurement of the photons, which means that Bob has a polarizing beam splitter and two kinds of polarizing beam splitters. One is a beam splitter. So Alice, depending upon her value of x, 0 and 1, prepares a photon in a particular polarization state. Okay, so she changes the basis of preparation. Bob, depending upon his value of x, we would like to call it y, suppose, whether it's 0 or 1, changes his measurement basis. So he uses two kinds of beam splitters. If Bob's input is 0, he measures in the cat 0, cat 1 basis. And if Bob's bit, the random bit is 1, he measures in the diagonal basis. So measuring at Bob's end could be of two kinds. It could use a beam splitter, which has two channels. One is the cat 0 channel and the other is the cat 1 channel. This is when x bob is 0. When x bob is 1, a different kind of beam splitter is used. Let's show that by blue. And this blue has two output channels. One is the 45-degree channel and the other is the 135-degree channel. In fact, in the lab, it's hard to get a polarizing beam splitter of this kind. So you rotate the state and put it in before a normal beam splitter. But that's a technical detail. I don't want to go into that. So this is the scheme that Bob uses. So if now Bob can get four kinds of photons. Okay. So if Bob gets, okay, you really have to be careful about this. If Bob gets a cat 0 photon from Alice and he's measuring in the rectilinear basis. So this basis here I'm calling the rectilinear basis, and this basis here I'm calling the diagonal basis. So if Bob is measuring in the rectilinear basis and he receives a photon in the state cat 0, then his output will be 0. Sorry. Which means that this detector here is going to fire. So if the input were cat 0, then of course this detector is going to fire with 100% probability. And if Bob received a photon in the state cat 1, the output will be 1. What if the input photon was a 45-degree photon and Bob was using this scheme here? What would be the probability that this detector clicks and the probability that this detector clicks?
Half.
Half each. So Bob cannot tell whether the bit that he received was 0 or 1. So each one of them comes with a 50% probability. So he's unsure, right? Likewise, if the measurement bases were diagonal, and one would input a state cat 0. Cat 0, if you notice, is strange. Cat 0 will be a superposition of 45 and minus 45 or 135. And cat 1 will be also a superposition. So you can use the same arguments here. So if Bob's measurement basis was diagonal and he received an input photon in the state cat 0, half of the times with 50% probability it will go to one detector, and with 50% probability it will go to the other detector. So Bob will not be sure whether the input is cat 45 or cat 135, but he will be sure in this case. So here, if an input 45 comes in, one of the detector clicks and he assigns an output 0. And if the other kind of photon 135 comes in, the other detector is going to click with 100% probability and he assigns a value of 0 to this. Sorry, 0 and 1. It doesn't really matter, but let's be consistent. So this is Alice's and Bob's scheme. So let's look at a practical example now so that everything gets clear. I know it's a bit tedious, but this is how these things mostly are. Suppose the key idea of BB84 is creating a secure key. So BB84 protocol helps you create a secure key. And if Eve tries to read this key or intercept this key or change this key, Alice and Bob will know with 100% certainty that the fidelity of their messages are being compromised, and they will discard that message and restart. So it helps detect attacks on data. So let's see how. Suppose Alice creates a sequence of zeros and ones. Let's call it A, this sequence A. And suppose this sequence is 1, 1, 0, 1, 0, 1, 0, 0. Now I'm going to describe how BB84 helps create a secure key, which if Eve tries to hijack it or intercept it, Alice and Bob will immediately know and they will be alerted. Okay. Now, X Alice is a random string of zeros and ones, totally random. Okay. 0, 0, 1, 0, 1, 1, 1, 0. So this is a totally random string of zeros and ones. Now we are still sitting in Alice's domain. Now, depending upon what input she gets, she chooses her basis. So let me draw the basis right beneath the sequence of zeros and ones. So 0 means the rectilinear basis, 1 means the diagonal basis, 0 rectilinear, diagonal, 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 rectilinear. Okay, so still we are within Alice's domain. Now what Alice does, she prepares a photon psi. All right, now since she wants to transmit, let me use a different color now. Since she wants to transmit the bit 0, and this comes with a random number 0, so she's in the domain, the rectilinear basis. She wants to send 1, so she sends a cat 1. A cat 1 is also, can also be written as a cat 90 degrees. So this is cat 0, can also be written as 0 degrees. This is cat 1, can also be written as 90 degrees. Okay, so she sends a photon in this quantum state cat 1. Here she also sends a photon in the quantum state cat 1. Here she's using the diagonal basis and she wants to send the bit 0. So she would send the bit 45 degrees. The photon will be 45 degrees polarized photon. Likewise, I can complete this. So cat 1, cat 45, cat 135, cat 45, cat 0. Okay, so she sends these photons to Bob. So here is Alice. She has a random number generator X. Then she prepares photons and sends them to Bob. So there is a sequence of photons. Cat 1, she first sends cat 1, followed by another cat 1, followed by 45, followed by cat 1, and so on. So this is time. So she sends a stream of photons. And this, since these are photons, they have to go on a quantum channel, like an optical fiber, which is less susceptible to noise. And then the photons are received at Bob's end. All right, now Bob also has a sequence, a random sequence X Bob. Suppose that sequence is a 1, so it's totally random, 1 1 0 1 0 1 1 0. So this is Bob's random sequence, totally random bits here. Okay, and Alice and Bob beforehand, they do not know their x's, they do not know their random sequences. Now what Bob does, Bob also has a prescription that and he has to measure in a basis depending upon his value of x. So if this is 1, he measures in the diagonal basis. If his bit is 1, diagonal basis, rectilinear basis, diagonal basis, rectilinear basis, diagonal basis, diagonal basis, rectilinear basis. And now what are his outcomes? Bob's outcomes. Now when Bob is receiving a photon in the state cat 1 and he's measuring in the diagonal basis, so a photon is coming in which is in the state cat 1, but the polarizing beam splitter is projecting along the diagonal basis states 45 and 135. What will be Bob's outcome? So a photon comes in the state cat 1 and Bob is using a polarizer which is in the diagonal basis. So one channel is the 45-degree channel, the other is the 135-degree channel. And if detectors are placed here, this corresponds to an output 0, and the detector is placed here, this corresponds to an output 1. Which of these detectors is going to click?
135.
Which one? Sorry, can you speak again?
135.
Uh, both of them have an equal probability of being detected, because cat 1, as you've noticed, is a superposition of 45 and 135. Okay, so cat 1, if it is input on a beam splitter of this kind, then it will go here with a 50% probability, and it will go here with a 50% probability. Okay, because you're not projecting onto cat 0 and cat 1, you're projecting onto some other basis states, on the diagonal basis states. So is this clear?
Yeah.
Okay, so the outcome could be 0 or 1, we don't know. Likewise here the outcome could be 0 or 1, but in this case the output is going to be a definite 0, because the input is, you see, the input here, uh, I'm sorry. So here are the photons that are coming in. This line shows the photons that are coming in. Okay, so in the third case, the photon that is coming in is cat 45, and still we are measuring in the diagonal basis. Sorry, in the rectilinear. Now we are measuring in the rectilinear basis. So the output could be 0 or 1. So for this photon cat 1, we are measuring in the diagonal basis. Still the output could be 0, 1. Here we are getting a photon cat 45, and now we are measuring in the rectilinear basis, so we are uncertain about the output. It could be 0, 1. But now we are getting a photon 135 degrees, and we are measuring in the diagonal basis, so the output will be 1. Here we are getting a photon 45 degrees polarized, measuring in the diagonal basis, the output will be 0, which means that this detector here is going to click if the input were 45 degrees. And now finally, if we were inputting a 0-degree photon and we were measuring in the rectilinear basis, what would be the output? What should I write over here?
0.
0.
0. Excellent. Now look at these three terms, 1, 0, 0. Let me reduce the size of the screen a little bit, even further. So what's happening is that if, so let me label these here. Let me label this here. So if I compare the random sequence of Alice with the random sequence of Bob, I'm comparing this thing with this thing. Both of these are random sequences. Okay. So here I have 0 at Alice's end, and at Bob's end I have 1. So Alice is preparing in one basis, whereas Bob is measuring in a conjugate basis, in a different basis. However, for the last three occurrences, both Alice and Bob are preparing and measuring in the same basis. So the bases match. All right. Their bases match. And when their bases match, would they be able to tell that this message that they wanted to send, only in these cases, Bob receives the same message or decodes the same message or retrieves the same message as Alice wanted to send in the first place. So this 100 becomes the secret key now. So this is how a key is generated. If Alice and Bob's bases, they match with one another and they advertise their bases to one another. After the photons have gone from Alice to Bob, Bob has done his measurements and he advertises to Alice what basis as he's chosen for the measurement. And Alice advertises the basis that he chose to prepare her photons, and she compares this information, share this information on a classical channel. Alice and Bob can agree, they can tell immediately that their bases match on the 1 2 3 4 5 6 7 8, that in the sixth, seventh and eighth photon that they receive, the bases match. They still don't tell what the outcomes are, but their bases match. So the photons that they receive here in the sixth, seventh, and eighth instance, though those will tell us that they have now generated a secure quantum key. Okay, so this is how secure quantum keys are generated. And if Eve would like to eavesdrop, now Eve has no mechanism of telling what the basis is, because the photons have already gone through and the key and the advertisement of the basis sets is done after the message has gone through. So Eve is looking at the photons. So she's trying to measure the photons and she's randomly orienting her basis between the diagonal and the rectilinear. If his basis matches what Alice's basis is, then fine. uh, he will get some result and he will recover the photon that Alice wanted to send, but it's not necessary that Bob is using the same basis for measurement. So only those elements terms in the sequence are important, which are 6, 7, and 8, in which the bases match. Sometimes Eve will be able to come up with randomly a basis on his end which matches either 6, 7, or 8. Then he could decipher what the photon state is. But then uh, the st- then Bob will be able to tell, both Alice and Bob will be able to tell that even though uh, their bases are getting the matching strings, they are getting disturbed and there's some discrepancy between the two bases that they have advertised. So this is the scheme of BB84, and I will probably send you some more. uh, it's already 3 o'clock. I'll probably send you some more tutorial, uh, one tutorial about BB84, and I will also write this up in a clearer fashion, so that you can understand what's going on. So at this point I would just like to stop here and uh, invite questions from you. I'll be happy to answer any questions about quantum information or quantum computation, anything from the 8 lectures that I've covered, and anything beyond that as well.
Assalamualaikum, Dr. Sabi.
Walaikum salam.
Dr. Sabi, I wanted to ask about is there a thing called quantum feedback controls? Because if there is a feedback control, has to be an output, and the output is like getting fed back. So if in the quantum realm, uh, the output when we measure it, it falls to one thing. So how can it be fed back? And is there a field called as quantum feedback controls? And for example, is there anything as quantum Kalman filters or any quantum fusion algorithms for that fact?
Which algorithms? Quantum?
Uh, Quantum fusion algorithms, sensor fusion algorithms.
So, Bilal, definitely. First of all, quantum control and quantum feedback is a very ripe field, and there are two kinds of quantum control. One is in which a classical measurement is done, and then the classical measurement changes the quantum gates. So this is a semi-quantum or a semi-classical control mechanism. Remember when I talked about quantum error correction and quantum algorithms, we introduced the idea of ancillary qubits. So
Yes.
ancillary qubits help in, you can measure ancillary qubits and feed the information back to your working qubits, and this information can be fed back in a classical sense like they do in teleportation, for example.
Okay.
So that is an example of quantum control, but there are examples of pure quantum control as well, in which quantum states are evolving on some space which is called Hilbert space, and it's not a flat space, and you could do geometric control with quantum states. So it's a very ripe field. And quantum Kalman filters, yes, they exist, and whenever lots of experimenters, when they would like to filter their data and use the measurement outcomes to improve the estimate of their quantum states, they use Kalman filters. And yes, we have quantum particle filters, we have quantum fusion. Compressive sensing, for example, is very ripe in the quantum field. If you would like to do single photon cameras, or single pixel cameras, and you just have a very few photons coming in, which are of course then quantum, then you would like to use compressive sensing and fusion algorithms and multiple cameras and multiple kind of sensors to recreate your image. So yes,
Oh,
there's a lot of overlap between these machine learning, between Kalman filtering and control. In
okay.
fact, control becomes really necessary when you would like to do large qubit quantum computing, because without control and feedback, it's hard to do error correction.
Okay. 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 So that means that at this time, if I try to interpret one of your statements, it's not real time at the moment. It's like the we take it classically and then do it, then
No,
do the feedback.
it could be done real time as well.
Oh,
Uh,
okay.
it could be done real time as well.
Okay. 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 Thank you, Dr. Sid. Thank you.
Yes. Any more questions?
I have a very basic question, Dr. Sabi, very basic question. But I want to ask that we always say that global phase does not matter. I just want to ask that does global phase affect the position of the qubit on blocks of air?
No, it doesn't. So if I draw the block sphere, let me draw this. Let me answer your question. If I draw the block sphere, sorry, it's not a nice sphere, but anyways. So this point here, suppose this angle is theta. This is my nominal x-axis, my nominal y-axis, and I make this phi. Okay. So this state over here is cosine of theta by 2 cat 0 plus sine theta by 2 ei phi cat 1. All right. So now if I add a global phase to this, ei say some chi. So this is a global phase. This chi is a global phase now. Now where do I lie on this block? I lie at the same point here. Okay. I don't go anywhere else. I keep. So this phase, global phase, has no bearing on where the state lies on the block sphere. It just lies at the same point. Some geometers, and if you study differential geometry, you would like to think of the global phase as a fiber on this block sphere. And in fact, the so you can ascribe chi to different points on this fiber. Okay. So this is a concept of in differential geometry, that your states are a fiber bundle, and your S2, which is the surface of a sphere, is a projective is a projection of the fiber bundle onto a lower dimensional space. But as far as practical purposes are concerned, if the phase changes, the global phase changes, you don't change your position on the block sphere. The projection on the surface of the sphere remains the same. So S2 is the surface of the sphere, and the position does not depend upon the global phase chi.
Okay.
I would like to ask a question related to this. It's a very good question because I was also struggling with it for a long time. Uh, uh, does the global phase affect when two quantum waves are interfering with each other? Because when we talked about the interferometer, it was actually the global phase and the sign that was caused by that. It interfered and it caused a deterministic result out of the end in the interferometer. So maybe it does not make a difference when you're talking about just one quantum state. But if you talk about two quantum waves, and in particular, when you talk about interfering of two quantum waves, does that make a difference then?
No, it does not make a difference whatsoever. Suppose I have a state psi, sorry, I have a state psi, and I find its overlap with another quantum wave, which is also a state phi, and I compute this modulus square. This is going to be the same if psi was had a phase with it. So ei alpha. So if I replace ket psi with ei alpha, and then I take the overlap with the same phi, this result is not going to change. So in interferometry, it was the relative phase between the two components of the superposition, the two basis states, which affected interference. The global phase can have a pronounced effect in other kinds of quantum experiments. For example, so I've answered your question, right? Now I'm going to give you one example of where the global phase can really matter. So, Mujtaba, do you agree with me that I've answered your question? The global phase is immaterial for interferometry. It's the relative
Okay.
phase that matters.
Yes. Yes.
Okay. Now let me give you an example of uh,
Actually, if you the answer that you're giving me, it's creative. I thought that somehow this relative phase was the same thing as the global one. I thought that when you
no,
take
no, no.
out the relative phase common out of the bracket, then you what you're getting is a global
You
phase.
cannot you cannot take the
Then,
relative phase common. The relative phase is someone which cannot be factorized. So cat 0 plus ei theta cat phi. This phi is a relative phase.
right.
However, what I could do, I could, and this is a global phase, ei alpha. Okay, so alpha is a global phase and phi is a relative phase.
Okay.
Okay,
Mm-hmm. Yes.
so what I could always do, I could write this as ei. I could take ei phi by 2 as common. I could put an e minus I phi by 2 here and plus ei phi by 2 here. So I could always do games of this kind, but still the relative phase is the difference between these phases here. It still remains phi.
Mm.
Okay, I can do all kinds of gimmickries, but still the relative phase is phi and the global phase is alpha.
Right.
Now let me give you an example of where the global phase can become important. So can you see my screen?
Yes.
Suppose I'm on a surface of a sphere, the block sphere, and I'm a qubit. Now look at my hand. Okay, I hope you can see my hand and my
Yes, sir. I can.
my fingers are pointing up. Okay, so I'm on the north pole of the sphere. Okay, and look at the direction of my palm. My palm is pointing towards probably your right.
Mm. Yes.
Now suppose I move on the surface of the sphere and I'm perpendicular to the surface of the sphere. So this is a sphere, I'm standing on the north pole. Now what I do is I move towards the equator and I always keep perpendicular to the surface of the sphere. Okay, I
Mm.
come down on the equator. Then I move by 90 degrees on the azimuthal plane. Okay, on
Right.
the equatorial plane, and then I move back to the north pole. Okay,
Right.
now has the direction of my palm changed?
Yes, it has.
It has changed. Previously I started off like this, went down, changed my phase phi, came back up to the same position where I started. So I've done a cyclic movement on the block sphere, but the direction of my hand, the arrow the direction in which my hand points has changed. So it started off here, I moved down here, then I moved along the equator, and then I came back here. So in the process, my hand was first pointing outward. Now it's pointing in this direction. So this kind of phase, which occurs because of transport on the Hilbert space or the quantum space, is called geometric phase. Geometric phase can be really important. It's also called Berry's phase. So there are lots of examples of quantum computing with Berry's phase and geometric phase. And this is a global phase. So
Right.
the global phase can become important when you're moving your states on the Hilbert space in an adiabatic fashion or through parallel transport. But that's beyond the scope of this course. So in some cases, the global phase can become relevant, but in most cases, it isn't.
Okay, if I may ask, I just got one more question. Does the relative phase have something to do with time and space? As far as I understand, because I even posted a question on the group, I didn't get any answers. I did an experiment on the simulations site that you suggested. What I did was that when you change the phase using a glass material, a glass piece, the probability changes in an interferometer example, of course. So that can only be in terms of this time and space, because the glass prism cannot actually change the direction of the polarization, or the direction in that case was just the direction that we were doing, that we're using as qubits. So does it have to do with the space and time? Is the relative phase somehow related to the space and time of the photon as well, the quantum wave? That's the question.
So the phase, so if you look at, forget about qubits, look at
Okay,
electromagnetic waves.
right.
Forget about qubits. No quantum mechanics has been invented. You're still in Maxwell's time. Look at electromagnetic waves. Electromagnetic waves are a wave in space and time.
Yes.
So if I were to draw, somehow my screen just stops working at the end. But let me just give me a second. This is an electromagnetic wave. Okay, now this is time axis, and I'm looking at the electromagnetic wave as a function of time, and I'm looking at the wave at some point in space, some fixed point in space. I'm measuring how the electric field is changing with time. So, right, so that's what the, now there's a phase associated with. If I were to draw another wave which is displaced in the time axis with respect to this, then this distance phi is a phase. Okay,
Yes. Right.
and this will of course be equal to omega times delta t. Okay, so if this is delta t, so this phase is connected to time. I could also draw this as a function of space at a fixed point in time. So these are spatiotemporal waves, and a photon is also a spatiotemporal wave. So the phase of a photon is indeed spatiotemporal. But when we're looking at the polarization of a photon, the polarization of a photon, in that respect, the phase has a different meaning. Uh, if I have horizontally polarized photons, which I could represent by this, quantum mechanically, I call them cat 0. Vertically polarized photon, I could represent them in a caricature fashion in this way and label them as cat 1. Then the phase difference between these photons is 90 degrees. So this is phase in terms of polarization states. And if I were to have a polarization, linear polarization in this form, which is at an angle theta, then my polarization would be cosine theta cat 0 plus sine theta cat 1. Now this
So
phase
yes, sir, I
phi
get this perfectly
is
now.
acting
But
like a,
I'm sorry, I'm cutting you because this is, I understand this now completely. There's a final question, just if you allow me, just one final question. So it's really that, you know, the theta, the angle theta is describing the qubit in reference to the basis set, sort of, yeah, the basis set, and the angle with respect to a measurement basis. Whereas the relative phase is related somehow to the magnetic wave of the photon, of the qubit in space and time. So if we already have these two angles to describe these two phases, angles, what we want to call them, don't you think that they're enough to describe the qubit? Why would we need a global phase in the first place? Why do we, what is the even purpose of the global phase?
So in some calculations, you've noticed that when we did the Deutsch algorithm, a global phase does appear, right?
Okay.
So it just comes out as a result of the calculation.
Mm-hmm.
Okay, so sometimes global phases also appear when they become dynamical phases. So time just clock clicks, time goes advances, and the global phase is picked up. So global phase, even though it's immaterial and inconsequential for measurement purposes, it comes out as a result of the calculations and to keep the physics consistent. For the geometric phase, I've given you an example of how the global phase, which is the geometric phase, can become really important. So if
Okay.
you have two qubits and one qubit is being adiabatically transported, it picks up a global phase with respect to this qubit, and this qubit can then interfere with another qubit, and in that way the global phase on this qubit will become a relative phase. So you just have to be consistent, and there are variety of problems that you are dealing with, so you have to be consistent with your physics.
Okay. Okay. Thank you, sir. Thank you,
So
sir.
any more questions from other participants? All right, Mosina, I think I would like to thank everyone here, and I will give the floor to you now.